On July 4th, 2012, one of the most important events in the history of science took place in Geneva. Surrounded by hundreds of leading physicists, the discovery of a new particle, the Higgs boson, was announced in the CERN conference hall, a particle whose existence had been predicted half a century earlier. A particle whose discovery marked a triumph for particle physics. The room erupted in applause. We had found the final piece of the universe's puzzle. But there was something strange about this discovery. I would even say something unpleasant. The Higgs boson is not at all what physicists expected to find. You see, the Large Hadron Collider, the facility that made the discovery of the Higgs boson possible, is the most complex machine in the history and perhaps the most complex thing in the entire universe. 27 kilometers of tunnels, the work of thousands of scientists over 20 years, and the tens of billions of dollars, all created for a completely different purpose. Originally, the collider was designed to discover new physics that lies beyond the standard model of particle physics, a set of theories reflecting the modern understanding of fundamental particles and interactions. Scientists had high hopes of finding evidence supporting new theory predicted as far back as the 1970s, supersymmetry. Supersymmetry was supposed to explain many of the mysteries of modern physics, where particle mass comes from, why particles have precisely these characteristics, what dark matter is, and whether is it possible to unify general relativity with quantum mechanics. Supersymmetry was not just one of several possible candidates for discovery. Physicists were expecting its confirmation above all else. It was the main hope. In a sense, the entire Large Hadron Collider project was convinced for its sake. Physicists were almost 100% certain that supersymmetry would be discovered. But in the same year, 2012, following the unexpected discovery of the Higgs boson, the scientific world was shaken by some very unpleasant news. No evidence in favor of supersymmetry was found. More than a decade has passed since then, and the situation has not changed. Even back then, it became almost certain that the theory would never see the light of day, and this is a major sign of the crisis that has befallen physics. The standard model is the most accurate theory in history. It explains all observable processes in quantum mechanics. It has no contradictions, it has no cracks, it is too good, and therein lies the enormous problem, because it was precisely behind these cracks that scientists were trying to find a new, deeper and truer theory of how our world is organized. After the failure of supersymmetry, there were simply no theories left in physics that could be tested. In December 2005, at the Solvay conference, Nobel laureate and one of the creators of the Standard Model, David Gross, uttered a phrase that was followed by a heavy silence in the hall. "We were wrong. We misread the signals, and now we don't know what to do." This statement would be cited in several major works and would mark what would later be called the nightmare scenario or the dark era of physics. According to Gross' hypothesis, all the physics over the past 50 years had been moving in the wrong direction, in a direction where humanity's most powerful tools had ceased to reveal anything fundamentally new, in a direction where we had reached the limits of our theories and our own capabilities, in a direction radically different from where physics had been heading throughout its entire history. Since ancient times, even before our era, science has operated according to a single pattern. When you see something you cannot explain, you come up with an explanation and test whether is it correct or not. All natural sciences, and not only them, are built on this. Physics was built on this as well. First the anomaly, then the theory that explains it. and physics successfully followed this path, but somewhere in 1970s something went wrong. In 2023, a paper was published in the journal Nature in which the authors analyzed 45 million scientific publications and nearly 4 million patterns published over the past 60 years. Among all the works, the authors specifically looked for those that described revolutionary discoveries that turned our understanding of the structure of the world upside down. It turned out that the number of such works had been decreased by 91%. There are more publications, more scientists, more funding, but fewer and fewer discoveries. If you open any physics channel on YouTube or any roundup of current physics articles, you'll see that, for the most part, the same few theories keep popping up in the one way or another. Supersymmetry, string theory, quantum gravity. These theories had been around for several decades, thousands of scientists are working on them, millions of people around the world discuss them, and enormous sums are spent on studying them. Yet there is no real benefit, because there's no experiment that could confirm or disprove these theories. Most likely, it is simply impossible. And then a logical question arises. What if theories that cannot be tested are inherently false? Which is precisely why they cannot be tested. What if somewhere out there, in a completely different direction of physics, there is indeed a theory that is not only capable of explaining the structure of our world, but can also be detected through observations and, in the future, lead to the development of even more fundamental ideas? And here is the main question that has been haunting me for the past few months, and for which I undertook this entire investigation. Why, after such a long and successful series of great discoveries, did we take a wrong turn? When did it happen? And is there even a right direction in physics? Today I will try to answer these questions and explain why physics stopped yielding fundamentally new knowledge precisely when it became so vast and powerful. Spoiler alert. This applies not only to physics. The causes of this crisis run much deeper than they seem, and in the future they will affect not only physics, but also mathematics, biology, art, and even how we think and perceive the world around us. Bern, spring 1905. A train is moving down the street. It passes one of the city's main landmarks, the Tsetglogi clock tower with its astronomical clock, and one of the passengers, looking at the tower through the tram window, asks the intriguing question: what would happen if the tram sped away from this tower at the speed of light? Even as a child, at the age of 5, this man expected his first real shock. His father showed him a magnetic compass. The needle, completely covered, stubbornly pointed north, as if guided by some intangible force. It didn't fit into my childish worldview, he recalled later, and it remains one of the most profound impressions of my entire life. This passenger's title was third-class technical expert. His daily task: to read patent applications and find technical inconsistencies in them. His tools: a desk with a stack of documents, and the daily rendezvous with Tsetglogi at the end of the workday. This man was Albert Einstein. He was 26 years old, and in the same year, 1905, he would publish 4 scientific papers that would lay the foundations for all of modern science. In the first paper, Einstein explains the nature of the photoelectric effect and introduces the concept of the quantum into physics, a particle, a portion of matter or energy governed by the laws of quantum mechanics. The second paper explains Brownian motion and proves the existence of atoms, particles of matter that had been predicted 2000 years earlier by the ancient Greek philosopher Democritus. In the third article, the author finds the answer to his question about a tram moving at the speed of light. In it, he lays the foundations of the theory of relativity, and finally, in the fourth paper, Albert Einstein presents the formula E equals mc squared for the first time, the most recognizable formula in physics. It is noteworthy, by the way, that the final paper containing the formula consists of only 3 pages, a paper with just 3 pages of text. In modern works, the bibliography is longer. And yet, even in such a short text, Einstein doesn't forget to include a brief acknowledgement section consisting of a single name, Michele Bessot, an engineer and colleague at the patent office with whom Einstein often drank coffee and discussed physics. He was not Einstein's scientific advisor, nor a sponsor of his research, just a friend with whom he discussed the clock tower and the tram. That's all. No matter how many times I've read these 4 works by Einstein, I've never paid attention to this detail. And only once did it take me think seriously, so much so that now you're watching this video. What allowed Einstein to so succinctly articulate ideas so important to science? A few pages of text that would become the foundation of all future science and change our understanding of the nature of time and space, without funding, without a lab, without a research advisor. And the point here isn't even Einstein's genius. Had Einstein not existed, someone else would have done it in a couple of years. The scientist himself acknowledged this. The fact is that physics and physicists have, so to speak, a judge. That judge was in nature itself. The special theory of relativity published in 1905 and the general theory of relativity which stemmed from it and was published in 1960 had a real reflection in nature. Just 3 years after the theory's publication, Arthur Eddington obtained the first experimental confirmations of Einstein's work. The theory predicted that light should deviate from a straight path when entering the gravitational field of massive bodies. While observing a solar eclipse, Eddington saw with his own eyes how rays of starlight literally changed their trajectory near the sun. There is an interesting pattern in nature. Species with short lifespans, bacteria, flies, mice, evolve at an astonishing rate. In a single year, bacteria go through hundreds of thousands of generations, and because of this, nature manages to test and weed out billions of variants in a short period of time. This is precisely why, by the way, bacteria develop resistance to antibiotics in a matter of weeks. The environment's response is instantaneous, and the feedback loop is very short. On the other hand, take elephants. One of their generations spans about 30 years. That is, to test a single experiment, a single mutation, nature takes billions of times longer than bacteria do. And no organism can adapt faster than environment's response. That is precisely why bacteria are so resistant. They adapt quickly. Science is, in a sense, the same kind of organism. Once upon a time, it adapted quickly to changes in the environment. As humanity developed, more and more new theories emerged, the picture of the universe became increasingly precise, and our understanding grew even deeper. At some point, we reached a peak, and that was it. To understand exactly what the problem with this stagnation is, we need to delve into the context of physics from the last century, to understand why modern physics looks the way it does. As you know, all the fundamental physics rest on 2 pillars. On the one hand, we have the general theory of relativity, the best available theory of space, time, motion, and gravity. The deepest insight of this idea is that gravity is closely linked to the geometry of space and time, which were previously considered absolute. Space is dynamic, it is movable and deformable. On the other hand, incidentally also thanks to Einstein, we have quantum mechanics, the theory of matter and radiation. Everything in our world consists of portions of matter and energy. They can be represented as particles or fields, and what matters is how they interact with one another. Material objects, such as you and I, can be represented as waves. We can determine the general properties and origins of chemical elements, and we can even describe the most complex system with a single formula. Each of these pillars, relativity and discreteness, remains incomplete. Each has its flaws, which point to the existence of a deeper theory, but the main reason for this incompleteness lies elsewhere. Reason demands a third theory to unify all of physics. And the reason is simple. Nature, in the obvious sense, is unified. All components of the universe are interconnected, and therefore we must assume that describing some things with one theory and others with another is simply illogical. Why should we ignore quantum mechanics inside black holes and not take gravity into account in the collision of light particles inside a collider? To address this question, scientists have formulated the 5 major problems of physics. Once we have answers to these, we believe we will be able to find the theory of everything. The first problem is the unification of the two pillars, general relativity and quantum theory. It is also known as the problem of quantum gravity. When we try to apply in one theory where another theory reigns, we encounter the central paradox of physics. When trying to describe the state of a quantum system at the moment of the Big Bang or the gravitational attraction between particles emerging from nothing in a vacuum, instead of meaningful quantities, we get infinities. When infinities appear in your equations, they stop working. The second problem is understanding the meaning inherent in quantum mechanics. Despite the standard model's success and its ability to explain a wide range of physical phenomena and processes, we don't really understand why the laws of nature behave exactly this way. Why does life behave both as a wave and as a particle? Why does the uncertainty principle exist? And what role does the observer play? Traditionally, researchers have assumed that science should provide an assessment of reality as it would be in our absence. Physics must be something more than just a set of formulas that predict what we will observe in an experiment. Science should provide a picture of what reality is really like. And the problem is that modern physics offers no answer to this question. Quantum mechanics is, first and foremost, a dialogue between the system and the observer. According to the laws of quantum mechanics, a system does not exist without an observer. Does the universe exist if there is no intelligent life in it? This question may seem silly to you, but physicists genuinely see it as a problem for which no solution has yet emerged. Personally, I believe that quantum mechanics is not a complete description of reality. In that case, we need to look for a deeper concept that includes quantum mechanics as one of its cases. As I mentioned earlier, this is a hint at a unifying theory. Albert Einstein can rightly be considered the first scientist to see a path to a unified theory in physics. Until his death, the scientist was engaged in the search for theory of everything, an attempt to unify quantum mechanics and the general theory of relativity. Einstein saw the main problem with unification as a loss. These theories exist simultaneously. In his view, we must distinguish between two types of theories: theories of principles and constructive theories. A theory of principles establishes a system of views on the possible description of nature. A theory of principles is universal. It can be used to describe anything. It is the fundamental language of nature. Therefore, in principle, there cannot be two different theories of principles in nature, since the world is united and everything interact with everything else. The problem is that quantum theory and the theory of relativity are two theories of principles. They are mutually exclusive. Another type of theory is constructive theories, which describe individual phenomena in terms of specific models. Electromagnetic field theory, quantum chromodynamics, and the theory of universal gravitation are constructive theories. They describe a single interaction involving specific physical processes, and they can be embedded within the context of a theory of principles. For example, the electromagnetic processes inside your computer are described by one theory, while the behavior of dark matter, which does not interact with the electromagnetic field, is described by another theory. There can be many constructive theories, and unlike theories of principles, they are not mutually exclusive. It is precisely the understanding of which theory is a theory of principles and which is a constructive theory that allows science to move forward. James Maxwell's realization in 1867 that the theory of electricity and the theory of magnetism are two different constructive theories, that they are two sides of the same coin, allowed him to conclude that there is a theory of principles governing these two phenomena. This is how the theory of electromagnetism emerged, and a century later, the electroweak theory, which described electromagnetic and weak interactions. The question is whether the remaining forces of nature can be unified according to the same principle. This is the third problem in physics, determining whether different particles and forces can be unified in the theory that explains them all as the manifestations of a single fundamental entity. It is important to understand that this problem differs from the problem of reconciling general relativity and quantum mechanics. In their attempts to solve this problem, physicists created the standard model of particle physics. It describes all quantum interactions as manifestations of a single law and classifies 24 particles of matter and radiation. And it predicts experimental results with incredible accuracy. However, for all its elegance, the standard model has one major problem. When we establish the laws of a theory, we must determine the coefficients by which processes and interactions occur. Constants form the basis of physical formulas. They also determine the properties of particles. Mathematics imposes no restrictions of the values of these constants, so they can take on any value, and we have no understanding of why the values of the constants are exactly what they are. Why is the electromagnetic interaction hundreds of times weaker than the strong interaction? Why does an electron weigh exactly that much? In the standard model, there are about 20 constants whose physical meaning we have yet to determine. And this poses serious difficulties. Behind every constant there must lie a fundamental fact that we fail to notice. Explaining how nature selects the values of the three constants in the standard model is the fourth problem of modern physics. In 1900, the British physicist Lord Kelvin said, "There is nothing left unknown in physics, except for two small clouds on the horizon." These clouds turn out to be the keys that, over the next 10 years, became the pillars of a new physics. Today, as we describe the entire material and immaterial world using general relativity and quantum mechanics, we also leave a gap in the form of two clouds: dark matter and dark energy. Overall, it seems to us that we understand gravity very well. With the help of the theory of relativity, scientists have learned to understand even quite exotic phenomena such as gravitational lensing, the effect of space being warped by matter. However, when several physicists in the 20th century attempted to measure the description of mass in the galaxy using two different methods, they obtained different results. The discrepancy reached 1000%. Moreover, this indicated that galaxies weigh much more than we think. There are only two explanations for this. Either we do not understand how gravity works, or there is something in galaxies that we cannot see and that contributes significantly to their mass. Scientists have dubbed this something dark matter. The dark matter hypothesis is most preferable, as it pales in comparison to the suggestion that the general theory of relativity might be wrong. Cosmology became more mysterious when scientists began calculating the behavior of matter while accounting for dark matter. Studying the dynamics of the universe's expansion, initiated by the Big Bang at the beginning of time, researchers discovered that despite all indications that the expansion should slow down and then reverse into contraction, in reality, the expansion was accelerating. The universe is expanding faster and faster, defying the laws of physics. There is only one explanation for this. There is an unknown form of energy with negative density. This strange energy was named dark energy. It later became clear that the entire observable cosmos, as described by two main theories, accounts for only 4% of its total content. Dark matter and dark energy make up 96% of everything that consists in the universe. And we still have not the slightest idea what they are. Explaining these entities is the fifth problem of modern physics. The 5 problems I described represent the frontiers of modern understanding of nature. It is on solving them that the leading projects at the forefront of theoretical physics are focused. And any theory that claims to be fundamental theory of nature must answer each of them. In the summer of 1979, the conference was held in the small town of Carriese, bringing together several dozen theoretical physicists to discuss pressing issues in fundamental physics. One of the speakers was Gerard de Hooft, a 33-year-old Dutchman. A few decades later, he would receive the Nobel Prize for his research in quantum field theory. For now, however, he was giving a lecture on a subject that might seem dry at the first glance. Imagine a physical system, a ball on a hill. If the ball is standing perfectly still at the top, the state is unstable. The slightest nudge and it will roll down. This position of the ball requires an explanation. Why is it there and why doesn't it roll down? In and of itself, such a state looks unnatural. A similar situation is observed in particle physics. In field theory, there are quantum parameters, numbers that determine the properties of particles, the mass of an electron, its spin, and so on. The problem is that we do not know the exact values of these numbers. When measuring, for example, the mass of an electron, we account for a multitude of forces acting on that electron from the external field of virtual particles. We know that these corrections are enormous, but it is impossible to measure their exact values. And here's the paradox. The mass of the electron that we measure is relatively small, and if we calculate the mass of the electron by adding its bare mass plus the contribution of all quantum corrections, we get exactly the same small number. Two gigantic values cancel each other out to within 34 decimal places. It is as if two numbers close to infinity, when subtracted, yield some specific small value. Physicists call this coincidence fine-tuning, and Hooft asks, is this a coincidence or have we overlooked something? He suggests that this coincidence is possible in only one case, when a new symmetry emerges in the theory. The symmetry, as it were, compensates for the corrections. I won't go into the details of the theory, that deserves a separate video. For now, the only thing that matters is that Hooft proposed the existence of a new type of symmetry. It called supersymmetry. The idea of supersymmetry is quite simple to describe. all particles in nature are divided into two classes: fermions, particles of matter, and bosons, particles of interaction. According to supersymmetry, every particle in one class have a superpartner in the another. Each fermion corresponds to its own boson and vice versa. It is precisely these superpartners that introduce quantum corrections that precisely compensate for the infinite contribution of virtual particles. Supersymmetry solved several of the 5 major problems in physics at once. It explained the origin of the fundamental constants, it provided a candidate for dark matter, the lightest superpartner, the neutralina. It creates a mathematical framework for unifying the 3 quantum interactions at high energies. Physicist Dan Hooper of Fermilab wrote the following about it: "Supersymmetry looks too beautiful not to be part of our world." Going back to the beginning of the video, the Large Hadron Collider was built for this very reason, and you already know how it all ended. The Higgs boson was discovered, and that's it. Not a single superpartner. Michael Kroemer, one of the leading experts at the Large Hadron Collider, said, "Looking back, it is amazing how long we kept repeating the same argument without thinking. 10 years, the same argument about naturalness." So what led the physicist astray? The theory's mathematics was elegant, the calculations were correct, and Hooft's reasoning was flawless. The problem lay elsewhere. Supersymmetry was not the only contender for explaining the Standard Model. Another project was running neck and neck with it, a far more ambitious one. In August 1984, American theoretical physicists gathered at the summer school in High Altitude Resort in Colorado for a semi-formal discussion of problems in theoretical physics. 2 of the participants, Michael Green of University College London and John Schwartz of Caltech, were working on equations that their colleagues considered dead ends. They were engaged in string theory. The idea behind string theory is just as simple to describe. All elementary particles are not points in space, as the Standard Model suggests, but rather tiny one-dimensional objects, something like vibrating strings. Different ways a string vibrates correspond to different properties of the particles, and so all particles are different manifestations of the same string. But string theory had one problem. Its mathematical framework was inconsistent. Technical inconsistencies arose within it, which Green and Schwartz attempted to resolve. And so, in their 1984 presentation, they announced the successful reconciliation of the theory's mathematical framework. But the ovation was followed by one remark: string theory is consistent only when space has not 3 dimensions, but 9. In the months that followed, the scientific community actively embarked on research in the field of string theory. Thousands of physicists were inspired by the idea that a single theory could solve all of physics problems at once. String theory unified quantum mechanics with gravity and explained the origin of particles and their properties. But years passed and the theory failed to develop. Moreover, it turned out that there were as many as 5 versions of a mathematically consistent string theory. It was not until 1995 that physicist Edward Witten managed to unify them into a single M theory, but then another problematic condition arose. The theory required that the 6 extra dimensions of space be compactified into tiny geometric shapes known as Calabi-Yau manifolds. There are an enormous number of such shapes. In 2003, physicist Michael Douglas attempted to calculate exactly how many valued configurations M theory contains. The answer he arrived at became one of the most cited numbers in modern physics, 10 to the power of 500. It is more than the number of atoms in the observable universe, many times over, and each of these configurations describes a separate universe, with its own constants and its own laws of physics. For science, such a discovery is a catastrophe. It is an uncertainty for which no one could find a solution. Whereas supersymmetry made specific predictions that needed to be tested, string theory made no predictions at all, or rather it made so many that any experimental result fit the description of string theory. And as it known well, the theory that explains everything essentially explains nothing. String theory cannot be tested experimentally. So what unites the two main modern theories of physics? At first glance, the answer is disappointing. Neither theory has made testable predictions. Both were based not on knowledge what the nature is, but on a belief about what it ought to be. Theoretical physicist Lee Smolin put it this way: we inherited a science that had progressed so rapidly that it seems to be a model of how science should work in general. Whether today or in the 1970s, our knowledge of the fundamental laws of nature has remained absolutely identical. It may seem that physics has reached a dead end, as if scientists simply chose the wrong path and can turn back. This is a reasonable conclusion, and it's almost certainly incorrect, because before accusing physicists of choosing beauty over truths, it is worth asking one question. Why did they decide in the first place that a true theory must be beautiful? This is not a mere assumption. Behind this conclusion lies a history spanning 3 centuries, a history in which beauty has proven right time and again, in which physicists trusting in mathematical elegance against all common sense discovered what they did not expect. And until we learn this history, we will not understand why the way out of the crisis is not as simple as it seems. Cambridge, January 1928. A young physicist, Paul Dirac, is trying to solve a problem that the most prominent scientist of the time had been working on. He was trying to reconcile quantum mechanics with the theory of relativity, more precisely, to apply the principles of special relativity to the Schrödinger equation, which describes the behavior of fundamental particles. The result of his reflection was an equation describing the wave function using 4 components. These components are divided into 2 pairs. The first pair corresponds to 2 states of the electron, with spin up and with spin down, but the second pair seemed superfluous, since it described an unknown particle with negative energy. When he consulted his colleagues, Niels Bohr and Werner Heisenberg, they advised Dirac to discard these solutions, since they had no counterpart in the form of real particles. In their opinion, these solutions were superfluous. But Paul Dirac did otherwise. He felt in his gut that the particles with negative energy in his equation did not appear for no reason. If a solution exists, then it must manifest itself in some way, and Dirac realized what they manifested in 2 states of a particle that had not yet been discovered, more precisely an antiparticle, an anti-electron, or in their words, a positron. In the scientific world, Dirac was always considered a bit strange. Albert Einstein said the following about him: "This man has always walked a dizzying tightrope between genius and madness." And despite his existing achievements in scientific circles, no one approved of Dirac's latest idea. Dirac created a mechanism explaining the origin and properties of his new antiparticle, later to be called the Dirac sea. He was also able to predict the conditions under which an anti-electron could be discovered. And so, in the summer of 1932, a young American physicist named Carl Anderson, while studying cosmic ray tracks, discovered a strange track bent by a magnetic field. At first glance, its shape resembled that of an electron track, with one exception: it was oriented in the opposite direction. That is, it interacted differently with the magnetic field. That could mean only one thing: the particle that left this track was the opposite of an electron, that is, was an anti-electron. This is exactly what the Dirac equation had predicted. This discovery would be the subject of no fewer than 2 Nobel Prizes in physics. And in the context of our video, it is interesting to note why the Dirac equation was able to predict the existence of a particle where no one expected it. As I said, this was no accident. The Dirac equation has a special structure. It was minimalistic and symmetrical, like a quadratic equation which always has 2 solutions. Its symmetry predicted the second solution corresponding to the positron. But the Dirac equation was not the only, or even the first, such instance of mathematics foreshadowing a discovery. In 1867, James Clerk Maxwell worked on unifying electricity and magnetism. He also formulated a set of equations describing the 2 phenomena, and these equations were almost symmetrical, but not quite. To complete this picture, one term was missing from the equation, but Maxwell could not find it anywhere experimentally. There was no practical reason to add it just for the sake of beauty. However, the scientist trusted mathematics and decided to add it to his work anyway. Initially, he did this solely to make the equation symmetrical. Only later did it become clear that the variable he added predicted the existence of electromagnetic waves traveling at the speed of light. 20 years later, Hertz would discover radio waves in his experiment. German theoretical physicist Hermann Weyl, one of the founders of quantum mechanics and the theory of relativity, wrote in a letter to Freeman Dyson, "My work has always sought to combine the true with the beautiful, but when I had to choose between the two, and usually I choose the beautiful." Weyl posited the beauty of a physical theory as a methodological principle. This principle allowed him to make a major contribution to the creation of the Standard Model. In 1956, Paul Dirac visited Moscow State University, where he gave a lecture on electrons and the vacuum. During his talk, the scientist wrote on the blackboard a phrase that has gone down in annals of physics: "Physical laws must possess mathematical beauty." Dirac had come to this conclusion on his own. Other scientists agreed with him. Their own experience also suggested that the nature seemed to strive for the beauty of its theories. However, here our story takes an unpleasant turn. The historian of physics Helge Krauss, author of the most detailed biography of Paul Dirac, wrote the following about this event. It is worth noting that the principle of mathematical beauty guided his thinking only in his later period. Precisely the one in which he, for the most part, did not produce physics of any value. To put it mildly, that sounds harsh, but it was the truth. Starting in 1935, Dirac shifted his focus entirely to the search for beauty in physics theories. He worked on the theory of magnetic monopoles, on new approaches to quantum electrodynamics, and even attempted to engage in quantum cosmology. The mathematics in his work was sophisticated. He was truly obsessed with the beauty of his own theories. And this gave rise to very bold assumptions. But there was nothing behind these assumptions. His ideas found no experimental confirmation whatsoever. Does this mean that beauty is not the primary source of truth? Why did beauty work in one case, but not in another? Theoretical physicist Sabine Hossenfelder explained it this way. Beauty in physics is almost always symmetry. Symmetry is the ability to explain more with fewer assumptions. If a transformation does not change the laws of nature, then it is symmetry. Symmetry eliminates unnecessary components and degrees of freedom. Ernst Mach called this economy of thought. When Maxwell added a symmetric term to the equations, it was not an aesthetic whim. It was an indication that behind the symmetry lies the real structure of nature. Beauty became a symptom of a deep order, but it was not always an indication of truth. In 1596, Johannes Kepler was struck by an idea. He wrote the following about it: "I felt as if God had revealed the secret of the universe to me." His idea was this: at the time of Kepler, the existence of 6 planets and 5 regular polyhedra, the so-called Platonic solids, was known. Kepler hypothesized that if one placed the polyhedra between the orbits of the planets, the distances between them would match the observed ones. Soon he would even write a book about this and call it The Mystery of the Universe. But later, Tycho Brahe's observations would show that Kepler's theory was incorrect. It was then that he refocused his efforts on finding the 3 laws governing the planets. It was thanks to these laws that Isaac Newton would develop his theory of universal gravitation. 71 years later, the German philosopher Johann Becher, while studying combustion processes, put forward his theory that all combustible substances contain a special substance, phlogiston. When burned, it is released into the air and creates fire. The phlogiston theory was elegant. It explained combustion, the oxidation of metals, and respiration. Chemists relied on the phlogiston theory for over a century. It was not until 1775 that Antoine Lavoisier, through a theory of precise experiments, discovered that metals do not lose mass when heated, but rather gain it. In other words, combustion is not a process of phlogiston release, but a process of oxygen attachment. I have now shown you 2 examples of how the beauty of a theory led scientists down the wrong path of knowledge. Hossenfelder, explaining why the idea of beauty in physics has once again become so popular, writes, "The successes of the past century are still fresh in the memory of those who stood at the origins of these discoveries, and their emphasis of beauty had a strong influence on the next generation. My generation, a generation that never managed to discover anything." In other words, this is the classic survivor's bias. Physicists extrapolated experience gathered under one set of conditions and decided to apply it to a fundamentally different field. The conclusion of all this seems to be this: beauty is not a panacea. It needs to be replaced with something more reliable, less subjective. But here history poses a question to which we have no answer. Imagine yourself as a physicist. You're faced with 5 unsolved problems and dozens of theories offering solutions. You need to choose a direction for your research. There is no experimental data that could point you in the right direction. You need some kind of selection criterion. Why, if not beauty? It's that they found themselves at a dead-end situation, a situation where they had no choice. Where this situation came from and why it happened specifically in the 1970s is another question, and a far more important one, for it is precisely this question that can help us find the right path to new theories and overcome the crisis of physics. In November 1974, in Brookhaven and Stanford, the same particle was discovered simultaneously independently of one another. The mesons existent confirmed the quark model and added another piece to the puzzle of the standard model of particle physics. This event later became known as the November Revolution. 9 years later, in 1983, The same accelerator discovered the W and Z bosons, which had been predicted 20 years earlier. Then, in 1995, the top quark was discovered. And finally, in 2012, the discovery of the Higgs boson completed the Standard Model. All these results were expected, and they led to a consequence that scientists could not even have imagined. Until 1974, physics allowed a certain logic. First an anomaly, then a theory to explain the anomaly, then an experiment to confirm the theory. Nature revealed something incomprehensible. Physics explained it. The loop was closed. But after 1974, it broke. The reason was very strange. There were no remaining ambiguities in the Standard Model that hinted at anything lying beyond it. In December 2005, at the Solvay conference, Nobel laureate and one of the creators of Standard Model, David Gross, said, "We were wrong. We misread the signals and now we don't know what to do." He had diagnosed the entire directions of physics over the past 3 decades. The man who drove science forward admitted that we have no way forward. Why did this happen? In short, because of all 5 of physics' unsolved problems exist on the Planck scale, where quantum effects and gravity become one and the same, where matter may behave fundamentally differently, where our universe originated, and to solve these equations, we need a new particle accelerator. You probably hear news from time to time about new particle accelerators being planned, 100 kilometers long or more, but let me say right away, they won't be of much use on a global scale. To reach Planck scales in experiments, a particle accelerator would have to be comparable in size to a galaxy. According to Heisenberg's uncertainty principle, the smaller the scale of interactions, the more energy is needed to absorb them. This isn't a technological limitation. Nature itself, as it were, sets the physical boundaries. It hides the universe's answers behind a barrier that is currently beyond our reach. Well, for now, most likely never. What can be done? Is it possible to find a new way to confirm theories, not through direct experimentation, but some other way? British physicist and mathematician Roger Penrose, a Nobel laureate in physics, set out to find the answer to this question. In the 1960s, together with Stephen Hawking, he mathematically substantiated the existence of black holes and provided that the Big Bang begins with a singularity. This is one of the most powerful achievements of theoretical physics in the second half of the 20th century. Penrose is a man at the very heart of science. He believes in its foundations, and this is precisely why he is particularly interested in resolving the scientific crisis. He described the states of modern physics in 3 words: fashion, faith, and fantasy. 3 diagnoses, 3 responses of physics to the disappearance of the yardstick. The first diagnosis, fashion, is a string theory. The second, faith, is quantum mechanics. The third, fantasy, is inflationary theory and the multiverse. Penrose does not criticize modern physics. He says everything has a positive side. Fashion doesn't rise out of a thin air. There is real mathematical depth behind it. Faith in quantum mechanics is justified by its colossal success. And imagination is sometimes the only way forward. If we don't dare to take what might seem like unbridled flight of fancy, we won't have any chance of understanding what might turn out to be a strikingly fantastic truth. It seems we've reached a dead end, but Penrose hints that we've been in exactly this same position before. Once upon a time, the object in question was considered fundamentally unobservable, and the best minds in science didn't believe it existed. And then one fact came to light that changes the entire meaning of this video. No way to see and no way to verify are 2 completely different things. Vienna, 1905. 59-year-old professor of theoretical physics Ludwig Boltzmann is preparing for another conference. He isn't worried about the quality of his prepared material. What concerns him most is the audience, or more precisely, one of the attendants named Mach. Throughout his career, Boltzmann had built the mathematics of heat on a single assumption. Matter consists of atoms, tiny particles that move, collide, and transfer energy. All the laws of thermodynamics arise from their collective behavior. His theory was elegant. Moreover, it successfully explained physical processes. The problem lay elsewhere. No one had ever seen atoms. According to most of the scientific community, science should describe only what is observable, and since no one had seen atoms, atoms were not science, they were metaphysics. I have just quoted almost word for word the words of Boltzmann's main opponent, the philosopher Ernst Mach, who spoke these words in the midst of this very lecture in 1903. All the Boltzmann's attempts to counter Mach's positivism were in vain. Mach was more authoritative and philosophically savvy. Mach twisted atomism into a realm of pseudoscience. It got to the point where Boltzmann, like Galileo, was forced to renounce his ideas, and only a small number of colleagues watched silently to see what would happen next. And things only got worse. Boltzmann spent the last years of his life in isolation. His health deteriorated sharply against a backdrop of depression. As a result, in 1906, Ludwig Boltzmann passed away. And now we know something that Boltzmann certainly did not know. Atoms exist. A year before Boltzmann's death, Albert Einstein proved the existence of atoms in one of his articles, using them to explain Brownian motion, the chaotic movement of countless dust particles on the surface of a liquid, something for which no explanation had been found for nearly a century. Einstein did not see atoms directly, but he saw the indirect sign of their existence. 3 years later, Jean Perrin confirmed Einstein's conjecture, and in this context, it is important to note the following. Einstein did not ask, "How can I see an atom directly?" He asked, "If atoms exist, what phenomena on the observable scale would be impossible without them? Can this question be applied to the Planck scale as well?" The year 1990. American physicist Raphael Sorkin of Syracuse University is working on the theory of causal sets. The idea is simple. Spacetime on small scales is non-continuous but discrete. It consists of several elementary events linked by causal relations. No coordinates, just the order of events. Sorkin applied Einstein's approach and asked, if this theory is correct and spacetime is discrete, how will this affect the scale of the entire universe? His answer, a cosmological constant must exist. Do you understand? Just 8 years later, two groups working independently of one another would discover the accelerated expansion of the universe. The cosmological constant exists, and even more surprisingly, the measured value of the constant matches Sorkin's prediction. Most likely, spacetime is discrete, and this didn't require a galaxy-sized accelerator. A telescope was enough. Sorkin's discovery remains the only successful prediction of quantum gravity made in the theory's entire 51-year history. The only one. Describing this episode in his book The Trouble with Physics, Lee Smolin writes the following. He distinguishes between two types of physicists: visionaries, those who ask fundamentally new questions, breaking the established narrative. Such scientists included Einstein, Boltzmann, and, for example, Sorkin. The second group, the craftsmen, those who brilliantly solve problems within the existing framework. They were essential, as they are the ones who primarily advance science, but it's the visionaries who bring about revolution. The problem is that the modern academic system is built around the craftsmen. It forces them to publish regularly, attend conferences, award grants only for straightforward and safe projects, and allows them to climb the career ladder only through technical excellence within the existing system. Pioneers, people who need time to think without being distracted by passing trends, are not welcome in this system. Smolin writes, "We need to change the system so that it favors Einsteins, people who think for themselves and ignore the established idea of influential colleagues." He is not calling for a revolution, he offers a diagnosis. Fashion, face, and fantasy dominate not only because the external arbiter in the form of the anomaly theory experiment loop has disappeared, but also because the conditions in which people capable of asking questions differently emerge have been vanished. What then should we do? Wait for a genius? Well, that sounds very encouraging. I don't really feel like relying on a chance and sitting idly by. Fortunately, history shows us that things will turn out differently. Newton, Maxwell, and Einstein did not appear by chance. They appeared when questions had been pulling up without answers for quite some time, when the contradictions within the theory became unbearable, when the old language was clearly falling and the new one had not yet emerged. Smolin writes, "We don't need a new technical result, we need a new way of thinking, one that is as far removed from quantum mechanics as quantum mechanics from classical mechanics." 50 years without fundamental discoveries is not stagnation, is the accumulation of momentum, the calm before the storm. The history of physics tells us such periods are not followed by gradual refinement. They are followed by a change in language. We're living in precisely such a moment, but one question remains. The question is not about the accelerator, not about funding for science, and not about trendy theories that aim to solve all physics problems. Bern, 1905. A tram passes the Zitgloggi clock tower. One of the passengers looks out the window and wonders, what would happen if the tram sped away from this tower at the speed of light? The question sounded absurd. No sane person of that time would have wasted their time on it. But this particular man was different. He had no laboratory. He had only a desk at the patient office, a stack of application, and a window overlooking the tower. We know how the story ended. Over the past 100 years, physics has changed beyond recognition. It has become vast, expensive, and complex. Thousands of scientists, billions of dollars in finding, dozens of kilometers of tunnels. It found everything it was looking for, and hit a wall. Not because we've gotten dumber, but because the answers to our questions lie where there is no direct path. Physicists, having received no clues from nature, turned to fashion, faith, and fantasy. They did not betray science, they adapted it to new conditions. In this time, Boltzmann found himself at the similar impasse, and he gave up, convinced he was wrong. A year later, someone asked the right question, not how to see an atom, but what would be missing if atoms didn't exist. Physics has always changed its language precisely when it seems that language no longer existed. Newton gave us absolute space. Einstein showed that space is not a stage, but a participant. Bohr and Heisenberg showed that nature does not exist in the absence of an observer. Each time it seems that we had reached the limit, and each time it turned out that we were mistaken. Perhaps today we are once again asking the wrong question. We ask, how to reach the Planck scale, when we should be asking about something else, exactly what that remained unknown. Because the right question arises when old theories have finally run their course. 50 years is enough time to squeeze every last drop out of the theories we have. Perhaps right now someone is sitting with a question that seems absurd to us, in the university library, in a cafe, in a rented apartment, not behind a lectern. This person has no answer to their question. There is no theory yet that can answer it. Those around them, observing this person's reasoning, view with skepticism, but somewhere deep down, in a glimmer of hope remains. What if it isn't absurd after all? We do not know this person's name. We do not know if he exists today or will be born in the foreseeable future, but we know for certain the right question does not await a solution. It simply cannot go unmasked.